Hi, my name is Gulletta. I'm a researcher at the University of Minho from Portugal, and I'm here to present our proposal work about continual learning of human-like arm postures. I would like to start with a brief introduction concerning the experiential learning cycle, which is very famous in behavioral studies with human subjects. This cycle is also known with the name of learning by doing paradigm, and it allows to create knowledge from the transformation of previous experience. It has been shown that recalling action is linked with the intentionality of a movement, which is often expressed with a grip type in pick and place tasks. In these kind of tasks, it has been shown that the selection of a target arm posture is performed by the analysis of a set of stored postures which have been obtained in past experiences of motion. In robotics, this is translated very often with the introduction of trajectory prediction methods, which are proposed to improve the performance of motion planners. These motion planners are often optimization based and may encounter local optima. This means that providing a meaningful initialization that is corresponding to the situation where the robot is moving is very important to provide high quality solution with a small computational cost. To the best of our knowledge, none of these prediction methods take inspiration from the human experiential learning cycle or to any biological learning system. The proposed method here wants to cover this gap in the current literature. In our previous work, we introduced a human-like upper limb motion planner, which is based on the selection of a target human-like arm posture. This means minimizing the angular jerk of motion, respecting some constraints in the operational space, avoiding collision with the obstacles, and avoiding the physical limits of the manipulator. Such a problem is solved by the optimizer IPOPT, which implements an interim point method for non-linear programming. This is a local planner. This is a local optimizer, which means that it may get stuck in local optima. So predicting meaningful initialization is very important to improve, to have a good performance of the overall planning system. Briefly, we want to formulate the learning problem, the mapping problem we want to address with the proposed work. We can denote with Q the set of parameters such as the target arm posture and the Lagrangian multipliers related with the constants of the optimization problem. C is the optimization cost returned by the optimizer, which is linked with the solution Q star, and the situation F, where F is a redundant geometrical descriptor. So to enhance the role of the initialization, we can also express Q star with the operator OF and the initialization Q init. So the purpose of the proposed learning method is to map a situational descriptor with a meaningful initialization for the problem of selecting a target arm posture. We also define two datasets, a cold dataset which is built with standard initialization offline, and a warm dataset which is built by one starting the optimizer in new situation, starting from solutions that are collected in the cold dataset. The warm dataset is also built after the definition of a refinement cost F, which is an index of how much refinement a solution needs when it is initialized with a certain initialization point, such as Qi in this case. Both datasets are updated with a time wait and forgetting strategy, which privileges more recent samples than old ones. We propose a locally weighted regression with a variable with kernel. The distance is a weighted distance, and the similarity metrics we want to train in each session are collected in the matrix W. The kernel sigma is variable because a fixed kernel could be either too small to achieve averaging data points or too big to achieve locality when data are dense, for example, very dense. And so sigma is dependent on a parameter r, which is initialized in every session with a parameter r0, which is close to 0.6 to place the kernel in its steepest slope, which is a good point when we want to fairly represent the samples in the dataset. Then at this point we can define the loss function we want to minimize to train our parameters. So the loss function, it depends strictly related on the expected value of the refinement cost. And then we have two regularizing terms which define the incremental nature of the proposed planner. Specifically, these regularizing terms guide the parameters to be as close as possible to their initial values, which are optimized, which are trained in the previous session. So incrementally, session by session, we can get a refinement of the training parameters. When training is done and we have an acceptable loss value, we can predict our optimal initialization given a new situation for the robot. So at this point we can have an analogy between the online experiential learning that we have in humans and our proposed method. Specifically, the stage of concrete experience is realized by updating the code of the warm datasets. Reflective observation can be realized by checking the loss value and evaluating some stopping criteria. Abstract conceptualization is actually the training process that happens on the updated datasets, and active experimentation is realized when there is the predicting on new initialization. There is the prediction of initialization on new situations. Sorry, and these active experimentations can generate new data to update the code and the warm datasets again. So to complete the cycle. We tested our proposed method on a simple scenario where we can find our humanoid robot Haros, which is equipped with a 7 degrees field manipulator and a barrel hand. We have a large red obstacle and a green target of the end effector. So on the right side we can see a successful target arm posture which places the end effector onto the green target and avoids collision with the large obstacle. So the forgetting strategy is tuned to obtain a size of the dataset of 19 samples, and we compare the performance of our method with the performance of a regressor with a simple Euclidean distance in the kernel. So what we can see that after 10 training sessions with 10 new situations on each session, we can see that the loss value in our proposed method is consistently smaller than the loss value when it is compared to the loss value of the regressor with the Euclidean distance. We have specifically after 4 sessions, in the first 4 sessions we have a pool feature extraction, but after that we have a consistent decrease, and the value gets stable to a value that is very small, very close to 0, which is acceptable. We can also have a closer look at the feature extraction. We can see that in the first sessions we don't have a strong feature extraction, but after session 5 and session 10 we can clearly see that we have the feature rank clearly tends to privilege the position, the orientation of the obstacle and of the target, and the relationship between the geometrical relationship between the target and the obstacle. When training is done, we evaluated the parameters on 500 new situations which have been uniformly sampled from the starting situation of the configuration of the robot and of the scenario. And what we can see is that our proposal method can clearly outperform other methods such as regressor with Euclidean distance and simply randomly a random picking of the solution in the code dataset. This is clear when we can see the number of iterations. When we see the number of iterations, the CPU time, the general cost, and we can also notice that the initialization that has been predicted by the proposing learner is very close to the actual solution. This means that predicting low-cost initialization also means predicting initialization that are very close to the final solution. To conclude, we can say that our method can provide high-quality solution at the minimum computational cost. This is done with a small dataset size, few training cycles, and online adaptability to new incoming situations. In future, we would like to apply different forgetting policies. We would like to design new situation descriptors which do not depend on the number of objects in the scenario, for example. And we would like to apply our learning method to human-like bounce posters which completely define collision-free human-like trajectories. Thank you very much for your attention.